Dan hiernaast Carolien, je achternaam Meerman, als vertegenwoordiger van onze samenwerking met de communicatiegroep. En namens het afstudeerbedrijf SINS is hier aanwezig Reken van Polen. Hartelijk dank voor al jouw inzet tot nu toe. Dus laten we Roelof succes wensen. Je weet hoe lang je nog spreken? Ja. Succes. Tot zo.
Okay, welcome everybody to my final presentation for my master's program of computer science, which is named All Roads Lead to ROMA. And the term ROMA in this sense stands for Robust Online Map Generation Algorithm, which is the algorithm that I developed during the research project. It's an algorithm which builds roadmaps of a dynamic environment, such as in the next slide. Dynamic environments can be found, for example, in disaster relief scenarios, where no up-to-date maps are available because there have been lots of changes to the environment. A map for such a situation would need to be constructed very fast so that relief workers can find their way to where they have to give aid as fast as possible. And a best guess is better than no guess at all. Also, the map needs to be able to adapt to new information. So if there are extra rock slides or trees falling over which make some roads unavailable, then you should also be able to see that in the map. We translated this practical setting into a research question, which I will show you on the next slide. After that, I will present the relevance of this research for the scientific world and the methodology that we used to approach the problem posed in the research question. This is then followed by the description of the algorithm and the experiments that we did with this algorithm to verify its working. And that's then followed by the discussion and the conclusion of this presentation. The research question for this research is how to create and maintain an accurate and dynamic map based on position traces. The term accurate in this research question is connected to that you want a best possible representation of the world. And dynamic means that you also want to have a quick response to changes in the world. And the position traces in this particular research project were GPS measurements of roads traveling on a map. Scientific relevance for this work is found in that it brings new insight into the dynamic nature of maps. Because most maps and most map generation algorithms that use GPS traces or GPS measurements to build a map, they take a whole stack of traces and say, okay, after we've processed all these traces, we see this as a resulting map. They don't say, well, after a first step we see this, and then we see this and this and this. And so there's not a lot of insight in the dynamics of the map, also not in when does a road cease to exist. When do we have to remove it from the map? So our project also gives a new description of the road decay. And because most of the map generation literature uses only visual inspection of the developed map against another known map, we added something to the field by creating a novel method of map comparison, where we compare two road maps to each other to see how good our developed roadmap is. For the practical setting, we add to the literature, or we add to the practical world, by giving a method which can be used in situations where there's no map beforehand, and that you want a speedy creation of a best guess. In our research project, we were thus interested in both the spatial and temporal accuracy of the developed map, where the spatial accuracy is how good does this map reflect the actual world, and the temporal accuracy was measured by looking at how fast or how quick does this map respond to changes in the world. We therefore simulated the world in which we made changes to the world, and we experimented with different densities of traffic. We used two experiments. The first experiment was for the introduction of new roads. So if you have no map at all, how fast can you create a map? The second experiment was then, what if you have a map and you remove some roads from the world? Then you expect that the quality of your map, as shown on the vertical axis, would decrease because your map does not really represent what the world is at that moment. But as soon as the map responds to those changes, the quality will go up again and will reach some kind of stable value. That were our expectations. I will show you later on how it went in the experiments. For the experiments, we used a simulated environment so that we could control all the independent variables that that I just discussed in the previous slide. The simulated environment was built on existing work of a PhD student at Almende, the parent company of Sense, where I did my research. And that is where we obtained our world model, which enables us to have a world, simulate traffic on it, and also simulate the removal of roads by blocking some of these roads. What we added to this simulator, this roadblock simulator, was a module for cartography, in which our ROMA module is built. And we also added an analysis module to be able to compare both the map representation of the world and our interpretation of this world based on the GPS traces that we obtained from cars and built in ROMA. So the left part is what we obtained from the PhD student at Almende, and the other parts were what I developed. In the simulator, we simulate traffic on a road map, which is the road map of Zoeterwoude-Dorp, a city of roughly 4,500 inhabitants. And the traffic is simulated by a kind of random traffic model, where you generate a car. You say this car travels from pick one point out of the map to pick another point out of the map and take the shortest route in between that. And roadblocks can also be added to this map so that the traffic has to take another route. This map representation has roads, intersections, and is therefore stored as a vector representation, or a graph in mathematical terms, which consists of nodes that represent intersections or endpoints of the road or of the map, and the roads in between are represented by edges. So now I'm going to tell you about what the algorithm actually looked like. I already told you that it's robust, that it responds to changes in the world online, so that it can process new information as soon as it becomes available. and improve the best guess that it has at that moment. And it uses simulated GPS measurements from the cars in the world and put them into the cartography module. It also provides a vector representation of the world, the same as, similar to what is used in the world. So this is the part where the algorithm is located. The algorithm follows a standard approach used in many map generation algorithms, where you start by pre-processing your incoming measurements by looking if they are suitable to use or not. And these measurements are represented in our work as the triangular shapes here, with the little circles around it showing the accuracy or the inaccuracy of the measurements, the standard deviation, as you can call it. Because GPS measurements, they have a Gaussian spread of the error in two dimensions, both in latitude and longitude direction. So on the horizontal plane, it's two-dimensionally Gaussian. Our map in the work is shown as these green squares with the lines in between, where the green squares are the nodes and the lines in between are the edges. Our pre-processing starts with a filter based on accuracy. It's not clearly visible on this screen, but this measurement has a rather large circle. So if the accuracy of a measurement is not good enough, then we throw away those measurements. And what remains then is only these 5 measurements. But then the second filter might say, well, these 2 measurements, they are a bit too far apart from each other. So we will look at the first section, and then the rest after this line is going to be looked at a later moment. So the trace is split at that point. We will then use the first 4 measurements from the previous example for path estimation, which means that we are going to look at what path in the map, in the existing map, is possibly taken by the traffic. We do this by looking for each edge in the map, how fit it is to be matched to a measurement. We do that based on the distance between the measurement and the edge, and the directionality of the edge and the measurement. In our example here, we use the columns E0, E1, E2, and E3 to represent which edges have been matched to the measurements in those columns, to keep it simple visually. We then apply a tree search, a forward tree search, which means that we take the edges from E0 and look at which of the edges and nodes could we have reached by using the length between the measurements as a limitation to how far we can search. So then the following graph remains, which is a tree, because it starts at one point and then branches out to other directions. Well, in the path generation step of the algorithm, we're then going to look at is it possible to find the best path? Well, in this example, there you have a best path because it fits the most of the measurements. And there we also see the advantage of taking a bit more measurements than just the first 2, because if we would have taken just the first 2, then we would probably have taken the upper road. But it can also be the case that no path is possible when there is one edge lacking in the map. In that case, we are going to have to look at how to make it possible for a car to drive from edges in E0 to edges in E1, because, according to our measurements, there was movement between those edges. It's still called a tree search, but we do it from each of the edges in E1, so then it becomes a forest, as we call it in mathematics. With this tree search and the tree search from the other direction, we're then going to look at where is the shortest gap between these two forests. And we're going to bridge that so as to make a road possible which still adheres to the length limitation that we got and travels the shortest route. Okay, with this edge added, we're returned to, well, a similar map, or the same map as in the earlier example. And then we take the first two measurements, so the measurement linked to E0 and the measurement linked to E1, and adjust all of the nodes in between, so which have been influenced by the traveling car. We do this by making projections of these nodes onto the line between the two measurements. At the location of those projections, we make interpolations of the measurements. So it's a derivative of the original measurements. We add those to the nodes, and that makes that the nodes are going to be changed, because each node contains a set of measurements making up the node's location. Now, what is new in our method is that we also looked at how can we make sure that the road, that the map doesn't increase all the time. So that can be done by merging some of the nodes, because due to the change in location of the nodes, they can also move towards each other. And then it might be that the two sets of measurements actually represent the same physical location, or that you're not sure that they actually represent two different physical locations. And if that's the case, by using a t-test, a Welch's t-test, because we have different amounts of measurements per node, and the standard deviation might not be the same. If the t-test says, well, this is probably not two different locations that you measured, then we will merge these two nodes and also merge the measurements in them. For the road decay, what we can do, because we know for each road when there was some movement over it, so when was there a car moving on that road, by taking all these measurements and determining the intervals between these measurements, we can then say, well, on average, we have an interval of this long between measurements. And because we also know the standard deviation or the variance of these intervals, we can then use a cumulative distribution function of a t-distribution to see how likely it is that a new measurement will occur before a certain time. Well, if a measurement has not been added in a very long time, so at the end of the graph, then we will say, well, okay, it might be possible that this road is no longer available. For example, if there has been a tree falling on the road, which changes that you can no longer travel on that road. Okay, so that was the algorithm, that was ROMA. Now we're going to look at how we compare the two maps. For this, we used a comparison method based upon the two graphs, actually. Here you see a map with the green squares and the world in blue circles. What we then did was look at we matched the nodes in the map to the nodes in the world, and vice versa. We did this by looking at which nodes are very near to each other. Then you you get a matching which looks like this. Then you see that the link between 1 and 1 and 4 and 4 is really clear. There are no other options at that point. But between 2 and 2, yeah, well, we might see that 2 and 2 are really on top of each other. But there's also, from the nodes number 3, they also think that for them, node number 2 is the nearest. So there we have a conflicting situation. We handle these conflicting situations by first looking at the matches that are made with the nearest nodes. So the match between 2 and 2 will be taken first, and then the matches from 3 to 2 and from 3 to 2 in the other direction are taken out. So that leaves us with 3 node matchings. With these, we can then determine the true positives and the false positives of in the map domain. The true positives are when you have match nodes in the world and in the map, and another set of match nodes in the world and in the map, and there's a road between them in both the world and on the map. The false positives are when there's only a world or an edge in the map. With these numbers known, or the lengths of these roads known, we can then determine the precision. Normally you would take the true positives and say we have this amount of true positives and we divide it by the amount of true positives plus the amount of false positives. But in our case we looked at the road lengths, so the edge lengths, and we used all the edge lengths of the true positives stored in the matrix M and divided them by the total length of the edges in the map. To compensate for the difference that you see on the right side in this picture, we also looked at the similarity between the edges in the map and the world, because an edge in the map can exist and there can also exist an edge in the world, but they might be of different lengths or different shapes. We used a simple similarity measure based on the difference in length. What we could also get was the false negatives from the world domain. This is when there is an edge in the world but not in the map. With that we could determine the recall value, and the recall value actually represents how much of the world has actually been represented in the map. Well, now we have these two values, but would be more ideal to say, well, our map has a quality of this number, so just have one number. We obtain this number by combining the precision and recall by taking the harmonic mean in the so-called F-score. We used the F-score, the precision and the recall to examine how our map develops over time. So now to the first experiment, road introduction. What you would expect is after the introduction of roads, after some time the map would stabilize or would get to a certain value and then no longer change that much. For 50, 100 and 200 simulated cars, we saw stabilization, but for more than 1,000 cars simulated, we saw that at some moment the precision values really went down, which implies that there's noise on in the map. These moments of overfitting, as they are called, were observed within 3.5 or 6.5 minutes, and were also coinciding with the maximum or the stabilization of the recall value, as I will show you in the next slide. Because what you see here is that after 5.5 minutes, you see that the precision value, the lower line, the blue line, is only sharply going down. And the recall value, although it's going up and down a bit, it is quite stable compared to the precision. For our simulations of 1,000, 2,000 and 4,000 cars, for the village of only 4,500 inhabitants, we obtained these values, or these moments of overfitting, within 3.5 to 6.5 minutes. So that's quite fast. So at that moment, you know the most that you can know about between which locations you can travel, because that is what the recall says. We took these moments of overfitting to start our second experiment. We then added roadblocks, which amounted to 10, 20 or 50% of the entire length of the map. And we then looked at how much time does it take before the map recovers, or how long it takes before the map gets back to the value that it would have when there would be no roadblocks added. We saw that it went faster for higher amounts of traffic, and I will show you in the next slide what that looks like. Here we only looked at the precision values, because precision is where you can see how fast the map will recover. Here we have the moment where we remove the roads, and the blue line here is where you have the experiment without any roadblocks. Then we have 3 different amounts of roadblocks, and clearly for the 50% of roadblocks you see that it goes down quite a lot, because half of what your true positives are no longer true positives. They are no longer matched to any road in the world, because the road in the world no longer exists. And what you then see is that all of these lines for the simulations with roadblocks, at some moment they reapproach the blue line. And they all do that within 25 minutes after the road removal in this experiment. In all the other experiments it was at least within 30 minutes that you could see that the road adapted to the changes in the world. I will now show you what that looks like in the map, in the visualization that I made. Here on the left side you can see the road introduction experiment, so without any roadblocks added. On the right side we now stopped the introduction of roads, or well, we blocked some of the roads. As you can see in the area with the circle around it, compared to the same area in the other slide, or in the other movie, that there's lots of roads being removed. And that is actually what you see when you see the recovery of the map over time. What you can also see is there's the noise that was observed in the measurements. You can see that by the thickening lines on the map, which are actually lots of edges very near to each other. So now after these experiments, I'm going to discuss what the novelties are of the method that we made, and what we now know about the noise, or what we expect about the noise that we observe, and the improvements that we can make for that noise. Well, the novelties in this method are that we have given a clear description of road decay, and how to make sure that your roads are removed as soon as you no longer get confirmation of their existence. We also investigated how this noise that we observed was formed. We could do that because the amounts of noise were different for different amounts of traffic. And we also provided the field of map generation algorithms with a graph-based method for map comparison. which is a bit more scientific than just looking at it and saying, oh, it looks good. Well, this noise, we assume that it's created by outliers in the measurements. Because if you, for example, have a road, and then you add some measurements to it, but one of the measurements is way off, then our algorithm thinks, okay, I cannot match this measurement to any edge that's here, because there are no edges. So I will create a new edge here, and then it will go back to there. If that's being done, if you do that quite often, as is done with higher amounts of traffic, then you will get more noise. And then you will see that there's many roads on the map where there's actually one road in the world. These measurements will then move towards the actual center line of the road because of the measurements distribution, which is Gaussian. Here you see when you have one edge, it will eventually end up in the middle of where the actual road is in the world. But if you have two edges representing the same road, then they will have to share all the incoming measurements. And the algorithm shares it based on, well, if you are left of the middle in this side, you will go to the edge on the left. If it's right of the middle in this situation, then you will go to the edge in the right. Well, there are many contributing factors to this noise. Of course, we use the simulation and a traffic model which might not actually represent the real world. We have to check to see if we have to validate it against real world data. The applied filters might be improved upon, and the static time to live that we used in the road decay. Because for road decay, you need an interval measurement. And when you have only one measurement, which makes up an edge, then you cannot determine that interval. So you cannot make the distribution function that I showed earlier. We therefore said, well, okay, if we have only one measurement, then we say, okay, take 15 minutes, half an hour, 45 minutes for this road to exist, at least. And if there have been no new measurements after that time, then you can throw it away. Yeah, the filtering methods can be improved so that outliers are actually better removed before feeding them to the rest of the algorithm. So now to the conclusion. Yeah, my research question. How to create and maintain an accurate and dynamic map based on position traces. In my conclusion, I say that, well, ROMA is a proof of concept, because in previous literature there's been not a lot of descriptions of how to make these roads decay over time. So the dynamic nature of this algorithm is actually new. And we made a proof of concept for the dynamic vector map generation in an online fashion, where you can add new measurements and thereby improve your knowledge of the world. Also, the framework for map generation evaluation that we made by combining this simulator where you can add roadblocks with our algorithm and the map comparison method makes that you can also evaluate other algorithms for map generation. In our future work, or in the future, we would like to see how to handle the map dynamics, especially with regards to the noise, in a more dynamic method. Because when you have these two edges next to each other, you might actually be able to see, in a similar way as we did with the node comparison, to compare if they are actually the same location. You can see if these measurements in both edges actually represent the same road. And if that's the case, then you might be able to combine them into one edge. But because the edges are all connected to other edges, it's not trivial to just put them together. We therefore say that this is meant for future work. We also think that ROMA can be applied in a distributed fashion. I will give you a quick example to see how that would look like. I use Bob and Alice, two very well-known names from computer science. Let's take Bob. Bob has a knowledge of the world. This is his map representation, and Alice has another map representation of the world. What if Bob and Alice drive towards each other? Bob drives from the left, Alice drives from the right. They meet each other a bit more towards Bob's side, where they have an overlap in their knowledge of the world. And Bob says, hey, this is what I know of the world. And Alice says, this is what I know of the world. If they combine these two sets of knowledge by either applying the trace merging method described in ROMA or by another method, then they can combine their knowledge into one new map. And this map is especially useful for Bob because Bob can now drive a shorter route towards the rightmost node in this map. So with this vision on the future, I'd like to conclude my presentation and thank you for your time.
Thank you very much. A lot of questions may be posed in English, maar het mag ook in het Nederlands. Dan kunt u ook vragen stellen.
Yeah, could you go back please? Well, first, thank you for your presentation. It's very interesting. Can you go back please to the recovery graphs?
The recovery graphs, yeah.
Yeah. One of these, yes.
These?
No, the next one, this one, yeah.
This one, yeah.
So here, you say recovery within 25 minutes. Is this computational time or is this real time?
This is simulated time.
Simulated time.
So it's the time that the actual cars in the world would take.
Okay.
Yeah.
Was not clear for me. It was computational time.
Yeah, no, it's...
Because you also have to be fast. So how long does it take to actually calculate this on your computer or PC?
Yeah, we weren't really able to make a decent estimation of this because the simulator also simulates the traffic and it takes all kinds of different calculations in it. So it was, yeah, we did not look into how much time the actual algorithm takes, but we can say that the algorithm has a time complexity, a quadratic time complexity.
Thank you.
Yeah, Melanie.
Yeah, thanks. It was really nice that you made it comprehensible for people like me who don't know much about computer science. I was wondering something. I know it's not really the core topic, but just because I was trying to imagine how are these measurements done in the real world actually? Because now I understand you work with a simulated world. How would it work in real life?
Okay, well what you can do in real life, each person that has a navigation system in his or her car or a mobile phone with a GPS sensor in it can then send these measurements to, well in this situation, a central place where these measurements are all processed and put into the map. But in a distributed fashion you would add them to your own map, and then as soon as you meet someone you will say, hey, this is what I know, and then the other says, this is what I know, and you combine it.
Ja, het was een interessante toog. Ik had eigenlijk meer behoefte vandaag aan de position locator voor een leeg parkeerplekje. Maar ik had later, ik van nou, je hebt ook schaaksituaties, dan moet je de kortste en efficiëntste weg naar de koning zoeken in een steeds wisselende situatie met blokkades en vrije openingen. Zijn de algoritmen in dit soort programma's vergelijkbaar met die in een schaakprogramma?
Dat is ver weg van het onder. Ja. Ik denk dat je daar vrij veel overzetting voor zou moeten doen om die twee domeinen aan elkaar te zetten.
Kun je er iets meer over zeggen?
Ja? Ik heb niet zoveel kennis van schaakalgoritmes, dus dat is wel lastig. Ja, wat je natuurlijk hebt als je een schaakspel hebt, zie jij op elk moment je volledige wereld. En is dus eigenlijk een ander soort situatie dan wat je hier hebt. Want hier doe jij continu kleine observaties van de wereld en heb je niet het totaalbeeld. Terwijl in een schaaksituatie zie jij het totaalbeeld. Het enige wat jij hoeft te schatten, hoeft te bedenken, is wat gaat de ander doen. En dus wat dat betreft denk ik dat ze vrij lastig te vergelijken zijn. Dus dat je hier zeg maar aan dit algoritme niet heel veel zou hebben in de schaakwereld en andersom ook niet. Ja.
Hi, thank you for the presentation also. I want to continue a bit on Melanie's point because you answered a question by explaining that, for instance, everyone with a mobile phone could contribute.
Mm-hmm.
Let's take, for instance, New York. Traffic jams are well known over there.
Mm-hmm.
How would you deal with that? Because you would still get information from every person in every part of New York, for instance, while actually the whole city may be blocked. And you would kind of try to circumvent it.
Yeah. Well, with the information, you also get an estimation of how fast the traffic goes on that road. And you can then use the information that you store in the map regarding this traffic speed at that moment to plan your route. So that you could say, well, I want to have the fastest route from A to B, and then you would automatically circumvent the whole jammed situation.
And the second part question, thinking just now of New York, how would you deal with such large amounts of data? I mean, big data is quite upcoming right now, but I'm not sure how many million people live in New York, but if you have them all constantly transmitting their GPS signals every, I don't know how often it's broadcasted, but how could you deal with that amount of data? Do you have any idea?
That's a good question. Well, what is usually done in frameworks for map generation based on GPS traces is that you gather all these traces and only make a real change to the map as soon as you have a whole stack of measurements that say, well, we've got something new, some new knowledge on this location. So that you would make the load on the map a bit less and do the pre-processing and the path estimation, that you could do that in a more distributed fashion.
Thank you.
But I would also think that this method is more suitable for smaller settings where you have only rescue workers on a difficult terrain.